Hey guys, in this video, let's go ahead and learn about ratios and proportions together. So let's jump right into it. Basically, there's some quick vocab we want to go over. So first we have a thing called a ratio. A ratio is basically going to use division as the operation to compare two different quantities using similar or same units. As long as they're in the same category, I think with some practice, you'll kind of see what I mean here, but it's basically very similar or same units. Then another type of ratio is a rate, but this one is basically a special type of ratio. This one is just talking about things with different units, and those ones are going to be a little bit more clear as well, and when we talk a little bit about examples as well. Now, what if you take a ratio and you set it equal to another ratio, or you take a rate and you set it equal to another rate? That creates an equation because there's going to be an equal sign between them. So I'm just going to go ahead and write a little equal sign over here to show that we're basically setting ratios equal to each other or rates that are equal to each other. So again, things that are equivalent. Okay. Next, we have this thing called a cross products property. This basically is a property with these proportions that says that if you multiply the diagonals of a proportion together, they will be equal to each other. So I'm not going to talk too much about that yet, but when we get to some examples, I'll show you what I'm talking about there. All right, so let's talk about ratios and how you can kind of read them or see them presented. Again, you are going to be comparing two different quantities, A and B. We have to make sure we do understand that B is not equal to 0. That's really important. I'm going to write that here using the actual algebra notation here. B is not equal to 0. Hopefully that makes sense when you look at this fraction form, because we can't really divide by 0. So we read all of these ratios using words, a colon, or a fraction form. We read all these as A to B, or A to B. So they're all read the same way. So try to refrain. I think a common misconception that people have in the beginning is getting used to the fact that this is not like A over B or A beats, if anyone maybe tries saying it that way. But if you see something as like a 1 to 2, it's not one value of 1/2. Like if you had half of a cookie, then half is one number, right? But when we're talking about ratios and rates in this context, in this unit here, we're really saying 1 of something compared to 2 of something else. So it's a little confusing because, again, it looks like a fraction, kind of smells like a fraction, it tastes like a fraction maybe, but it's not really a fraction. It's just in a fraction form, but we're talking about called these ratios or rates here. Okay, so hopefully as we practice, it'll get more comfortable. All right, so let's go ahead and practice writing ratios real quick. Orly has a pile of Sour Patch Kids, one of my favorite candies, and she specifically has 24 blue ones, 16 red ones, and 18 green ones. So we're going to go ahead and find the ratio of blue to red in all three forms. So it doesn't matter which one you start with, but blue must come first and red must come second. So I'm going to start off by writing the ratio in fraction form. These are going to be ratios because Sour Patch Kids and Sour Patch Kids are similar types of units, right? Or same units. So we have 16 to 24. Again, this is not an improper fraction. It's just comparing these two values. We should always simplify before we write the three forms. We can divide top and bottom by their GCF of 8. So we can say this is a 3 to 2 ratio. For every 3 blue Sour Patch Kids, there are going to be 2 red Sour Patch Kids. So this is 3 to 2 in fraction form. In word form, this would be 3 to 2. Up to you what order you want to write them in. And then using a colon, we can say 3 to 2. All right, so in all three forms here, this would be the ratio of blue to red. Just make sure you always simplify before you write the 3 different forms. What about if we want to go from, let's see, it says ratio of all Sour Patch Kids that she has to green. So all means we have to add them all together. So 24 plus 16 is 40, 40 plus 18 is 58. So I'm going to start off by writing this in fraction form. So there's a total of 58 of them. And how many green ones are there? Well, there's 18. So if we simplify this based on their GCF of 2, that's going to be 29, which is prime to 9. They have no common factors, so we simplified already. So in word form, this would be 29 to 9. And in colon form, you could say there's a ratio of, for every 29 total Sour Patch Kids that Orly has, 9 of them are going to be green. Okay, so that's all three forms. For this third example here, it says find the ratio of red to green Sour Patch Kids. It doesn't say write in all three forms, so you can pick a form of your choice. I'm going to use a colon here. Let's see, red to green, so I believe that's going to be 16 first. Green is going to be 18, so it's a 16 to 18 ratio. But you can also simplify by the GCF here, so we have an 8 to 9 ratio here. Okay, so for every 8 red ones, there are going to be 9 green ones, which makes sense because there's more green than red that Orly has here. Then for this fourth one, it says find the ratio of green to red and blue Sour Patch Kids combined. So before the word 2 here, you can see green. So green is going to be 18. I'm going to go with 18 first. But then it says, I'm going to use fraction form, but do whichever method you prefer or which form you prefer. It doesn't say to write all three. It says red and blue combined here, so we have to take those numbers and add them together. So that's going to be 16 plus 24. So 16 plus 24 is going to be 40. So this is really an 18 to 40 ratio. But we can divide these numbers both by 2, their GCF, and say that's going to be a 9 to 20 ratio. Okay, so it doesn't say you have to write in all three forms. We just wrote it in fraction form, so you can just leave it just like that if you'd like. Basically, this says for every 9 green Sour Patch Kids, there are going to be 20 in total that are blue and red. All right, now that we know how to write and represent ratios a little better, let's talk about proportions. So again, we said earlier that proportions are essentially an equation. Equations are going to have equal signs, right? So let's just kind of make sure we remember that. And it shows that two ratios are equivalent, which another reason why we're using equal sign, because equivalent means we are saying it's equal, right? So the general form, this is what a proportion looks like, is this A to B ratio or rate is equal to C to D, another ratio or rate. And we can also write it like this. So sometimes people are going to see it written in colon form as well. So a ratio of A to B is equal to the ratio or rate of C to D. So you can write it either way, whichever you prefer. Just keep in mind again that B and D can't be equal to 0 just because those are the denominators of these ratios and we can't divide by 0. Okay, so these are proportions. And then something we mentioned earlier was the cross products property, and I'll kind of just take note of that here and just go ahead and write, if we have this ratio of A to B is equal to C to D, the cross products property essentially tells us that if we multiply these cross products, so the product of B and C, if we go ahead and multiply B and C together, it's going to be equivalent or equal to the product of the other cross products, which is going to be A multiplied by D. All right, so these are called cross products. One of the cross products is B times C, or BC, and the other cross product here is A times D, or AD. All right, as long as you have 3 of the values of a proportion, you can solve for the fourth one if it is unknown. So let's go ahead and try practicing that now. All right, so I have a few different methods we can talk about here. So for method 1, let's go ahead and just apply the identity property. So this one's kind of nice. So check this out. Let's go ahead and write down the proportion here. So we have 11 to 6 ratio or rate. That's equal to something to 30, right? So using the identity property, that means if you go ahead and multiply something by 1, it's going to stay the same, right? So on the left side, we have this ratio that we know both values of. We don't know the values of both of them on the right side. So let's not start there. Notice here that if we multiply this ratio top and bottom by the same number, then it's going to essentially stay the same, right? So what we can say here is let's take this 11 over 6. Let's multiply it, let's say, by 1. But let's be a little more specific about what values to use to represent 1. I'm going to use 5 over 5, which I hope you agree is equal to 1. And so let's see what happens if we go ahead and do that. Now, again, this is really just 1, right? Just a nice version of it. So why did I choose 5 over 5? Well, if you go ahead and multiply 11 to 6 by 5 over 5, we're essentially going to get 55 to 30, which again is the same ratio, just larger numbers, and that's going to be equal to x to 30. Now what's nice about this is you can see here that because these denominators of the ratios or rates are equivalent, then that must mean that the numerators must also be equivalent as well. So this must mean that x must be equal to 55. So if you can ever see that the denominators are easily able to be made the same number, or the numerators, that can make solving these proportions pretty straightforward. So if you ever see that, go ahead and use it. Let's try another method. For method 2, let's apply the multiplicative inverse property. So let's go ahead and just write this proportion down. We have something to 8 is equal to 5 to 12. And try reading it in your head that way or out loud so you get used to seeing these as ratios, comparing different quantities as opposed to fractions. The multiplicative inverse property, well, let's see, we have a 1 over 8 here, kind of as the coefficient for x, right? So using the multiplicative inverse property, we would multiply the left side of the equation by 8 over 1. That's the multiplicative inverse of 1 over 8. And let's do it to both sides of the equation here to keep things consistent. So on the left side here, these reciprocals are going to cancel out here. So these 8s are going to become 1s because 8 over 1 times 1 over 8 is just going to be 1x. So I'm I'm going to say 1x is equal to, and on the right side here, let's go ahead and cross cancel before we multiply. 8 and 12 can both divide by 4, they're GCF, so we're going to get 3 and 2. And so 1x is going to be equal to 5 times 2 is 10 over 3 times 1 is going to be 3. So 1x is equal to 10 over 3, and we could also say that x would be equal to 3 and 1/3. This would be the value of x that would make this proportion true. Okay, hopefully that makes sense, just because 5 is a little bit smaller than half of 12, and you can see this 3 1/3, if you plug in right here, that's a little bit less than half of 8, so these ratios are equivalent. All right, cool. Let's try a third example. In this case, let's try method 3, which is actually using this new property called the cross products property, if it's new to you. Basically, if you take this ratio of 5 to x, and that's equal to 9 to 4, let's go ahead and just use the cross products here. The cross products property says that if we go to multiply 9 and this x together, 9 multiplied by x, or just 9x, that must be equivalent to the products along the other cross product. So that's going to be 5 times 4, which is going to be equal to 20. Okay, you're still going to have to use some properties of equalities here. Essentially, you can divide both sides by 9, or you can multiply both sides by 1/9 if you want to use the multiplicative inverse property. And you're going to say here that 1x is going to be equal to 20 over 9. Again, don't overthink the 20 divided by 9 part. You can say that x here would be equal to, and you can leave it as an improper fraction or turn it into a mixed number and say it's going to be 2 and 2/9. If they're application word problems, I think mixed numbers make more sense. But if they're just these kind of rote problems where you're solving them, I think improper is also okay. All right, this one's pretty situational here. If you take a look at this proportion, notice that we have both values on the left side, but that you actually can simplify them, right? So if the numbers are getting bigger, always check to see if you can simplify by a GCF on one side, just to make your life a little bit easier, right? So you could use cross products right away, but notice 16 times 18 is kind of a large number, right? So I'm going to go take a look at this 24 and 18. I think their GCF is 6. So if you divide these both by 6, notice how that's just going to be 4 to 3 is going to be equal to 16 to x. And you can use whichever method that you want to at this point, but I think my strategy I'm going to see here is I'm going to say, oh, I could multiply and use the identity property here, right? Because if you notice here, 4 and 16, they kind of go in nicely. 4 is a factor of 16, or 16 is a multiple of 4. So if you go ahead and multiply top and bottom here by 4 using the identity property strategy, we can say that 16 over 12, 16 to 12, is equal to 16 to x. Well, what does that mean? That means if 16 is equal to 16 on top, then x must be equal to 12 on the bottom here. So that would be the value of x that would make this proportion true. So simplifying first can definitely make your life a little bit easier. All right, what if we have some expressions here? So notice over here we have not just x, but we have this x minus 3. So this one's situational, but remember that there are implied grouping symbols with fractions, so this part is going to be grouped together, right? I'm not going to write it, but you should know that it is there. Now in these particular scenarios, I think cross products is going to be probably the most straightforward way to solve these. So let's go ahead and find the product of 112 and x minus 3. So we'll take this 112 and multiply it by the quantity of x minus 3. That's one of the cross products. Make sure you include the grouping symbols like here. And then on the other side, the other cross products is going to be 7 times 8, which is going to be 56. Okay, so this equation is true just because of the cross products property. You can do one of two things here. You could use a POE right away, or you can use a distributive property. I'm going to go ahead and use a distributive property because I think that's what more people would maybe do first here. So 112 times x is 112x. 112 times this negative 3 is negative 336, and that's going to be equal to 56. Now, if you use the addition property of equality and add 336 to both sides, 56 plus 336 is going to be 392. So I believe we can just say 112x is equal to 392. And if you take this 392 and divide by 12, 112 on both sides, we're going to get x is equal to 3.5 here. Okay, so up to you how you kind of want to do this, but if you want to use long division or you want to simplify fractions, kind of up to you. I was thinking in my head here that this 392 divided by 112, I was thinking what common factors do they have, and you can think about like some different types of things that you could divide them both by. What I was thinking in my head was maybe just divide both of them by 4, and I was thinking 98 and 28, I think I was thinking, and then I divided these both kind of by 7 here. And then I was thinking if you divide these both by 7 here, we're essentially going to be getting 14 over 4. And then I knew that went in 3.5 times. So that's kind of what I was thinking. And so the solution for x in this particular proportion here is x would be equal to 3.5. Now, if you wanted to check this, you totally could do so. You could take this 3.5 and substitute it in for x. So basically 3.5 minus 3 would be 0.5 over 8, or half over 8 would be the same ratio as 7 to 112. All right, let's go ahead and check out some application problems real quick together. So in example 3, we see here that if Owen can run an average of 12 miles per hour, this is going to be a rate, not a ratio, just because we have different units. And he does this for 20 minutes straight. So that's on average, he's running 12 miles per hour. The question is how far can Owen theoretically run if there's 25 minutes? Also, how far could he run if he only has 5 minutes? All right, first thing we're going to want to notice here is that this is going to be in 12 miles per hour. And you can see here that everything else here is kind of in minutes, right? So we have different types of units. So I'm going to just start by converting units and write equivalent rates here. So I'm going to write 12 miles, and that's in 1 hour. So I'm going to write this as a rate. And let's see, we want to have the same units. Hopefully it makes sense that 1 hour is the same thing as 60 minutes. Those are equivalent, right? So we can say this would be 12 miles in 60 minutes, right? We could write that as a rate, but this time we have units that are more helpful for this particular problem. All right, now that we have everything kind of in minutes here, we have 20 minutes over here. We also have this 25 minutes. We have this 5 minutes. Everything is kind of in the same units of minutes, so that's good, right? So let's go ahead and go on to step 2, which is set up a proportion to solve. So let's take care of the part where we want to see how far can Owen run in 25 minutes first. So let's go ahead and use this rate that we came up with here, this 12 miles in 60 minutes. Let's go ahead and use this part here. All right, so we have this 12 miles in 60 minutes. Let's go ahead and set that equal to, well, we want to find out what's he going to be doing in 25 minutes, right? So 25 minutes, let's keep the units together here. So 25 minutes, the minutes are on bottom. We want to see how far he can run. Well, distance is on top here. So let's go ahead and say let x represent how far that Owen runs here, all right? All right, now let's go ahead and solve this proportion and figure out how far Owen can run in 25 minutes. Now, first of all, I'm noticing here that these two values have a GCF of 12, I believe. I think we can divide top and bottom both by 12 to make these numbers smaller. If that's true, we're going to have a 1:5 ratio, or rate here rather, right? And that's equal to x to 25. I guess there's a few different ways you could do this, but I'm noticing right away that maybe using the identity property is kind of nice here. If we multiply top and bottom by 5, we're essentially going to be getting a 5 to 25 rate is going to be equal to x to 25 on the other side. So we know here that x is going to be equal to 5. So this means that if Owen can do 12 miles in 60 minutes or in an hour here, if he was given 25 minutes, we would expect him, assuming all variables stay constant here, that he would be able to do 5 miles in 25 minutes. All right, so we just figured out what he can do in 25 minutes. Let's see if we want to figure out what he can do in 5 minutes. So let's see, we know initially that Owen can do 12 miles in 60 minutes. But let's go ahead and see if we want to find this out in how far can he go in 5 minutes. This shouldn't be too bad based on what we have found already. Same thing, we can go ahead and simplify this rate over here to make that a 1:5 rate. So 1 mile in 5 minutes. But wait, we're actually looking for that. I think we have how far can he go in 5 minutes. So we actually already know. So x would be equal to 1. All right, so how can we go ahead and interpret these two answers of x equals 5 and x equals 1? And so let's go ahead and interpret what we found out here. So for the first part, or the first proportion we solved, we can go ahead and conclude that Owen can run 5 miles in 25 minutes. And we can also say, and 1 mile in 5 minutes. All right, again, this is all assuming that all the variables stay constant and Owen doesn't get tired or anything like that, but that's what we have to assume in these particular problems. All right, let's go ahead and try another example together. All right, so in this example, we can see here that we have a car that's traveling 50 miles per hour. It's going to travel 15 miles further in the same amount of time as a car that's traveling 30 miles per hour, which hopefully makes sense. If they have the same amount of time, the car that's going faster is going to travel further in the same amount of time, right? So we're going to go ahead and find the distance that each car travels. We have this equation here that is really important, which is distance equals rate times time. With practice, this equation will hopefully make more and more sense to you as you practice it and apply it. D is always going to be representing a distance. R represents a rate or a speed, and then T is going to represent time. So let's go ahead and see what kind of variables we want to define here. All right, let's start off by saying here that all right, so defining some variables here, let's start off and say that let's let R represent the rate, and that's going to be how fast a car is going. Let's let T represent time, and we know this is going to be the same for both cars. They're getting the same amount of time. But then we have D, which is going to be representing the distance. Now there's two distances I guess we have to talk about. You could either call D the distance for the faster car or the slower car. I'm going to say distance traveled. You can define which one it is, but I'm going to say distance traveled for, I'm going to say the slower car. Your choice though, okay? But I think this is going to be a little bit easier to do. All right, so now that we have our variables defined, let's go ahead and set up an equation for the first car. Now for the first car, I guess we should define what the first car is going to be as well. The first car, I'm going to go ahead and say this is going to be the slower car, okay? And then we'll do the faster car in just a moment. So for the slower car, let's see. We have this equation we said earlier, which was distance equals rate times time. So I'm going to go ahead and write that down. Distance is equal to rate times time, where D is equal to RT. Do we know the distance traveled for the first car or the slower car? I don't think so. So let's go ahead and say D is equal to. The rate of the slower car we know is 30 miles per hour. So that's going to be 30. Multiplied by time, we don't know how long it's going to be taking, so it's going to be 30 miles per hour, and time is going to be representing that, right? So that's going to be one equation. For the second one, let's go ahead and say this is going to be for the second car. This one is going to be faster. So let's go ahead and write this down. Let's write an equation for the faster car now. Okay, so for the faster car, this one is also going to have this equation. Distance is equal to rate times time. Do we know the distance traveled for this one? Well, the distance traveled for the faster car is going to be whatever the slower car did plus 15 more miles. So we're going to say we're going to have D plus 15 just because it's traveling 15 miles further. And it's going to be 50 miles per hour. So the rate is 50, and we don't know how much time went by, but we do know that the T in this equation is the same as the T in the last equation. All right, now notice here that we have T in both of these equations. We know they traveled for the same amount of time. So what if we went ahead and just rearranged this equation over here? What if we divided both sides by 30? If we divide both sides by 30 here, we can see here that T, or the amount of time, would be equal to the distance divided by 30, right? Hopefully that makes sense. If you divide this side by 30 and you divide this side by 30, we can see that these 30s would cancel out to make 1, or 1t, and then D over 30 is what we kind of have right over here. Now, what about the second equation here? For the second equation, what if we want to get this T alone? Let's go ahead and divide this side by 50 and divide this side by 50. If we go ahead and do that, then our equation would say T is equal to the distance plus 15, because it travels 15 miles further, divided by 50, okay? Because it's going a faster speed here. All right, let's see here. Now, if this T, or the amount of time, is the same for both of these equations, right? Because both cars are traveling for the same amount of time, then we know that if time is equal to this distance divided by 30, and time is also equal to this distance plus 15 divided by 50, then we could go ahead and use substitution and say that this expression must be equal to this expression right over here. So using substitution here, we can go ahead and say that D over 30 must be equal to D plus 15, or the distance plus 15, divided by 50. Now I'm going to go ahead and use cross products here to go ahead and solve this proportion. So I'm going to go ahead and multiply this first cross product is going to be 30 multiplied by the quantity of this D plus 15. Make sure you input those parentheses because of the grouping symbol. So that's one cross product. And the second cross product here is going to be D multiplied by 50, or we can say that's going to be 50D. All right, so using cross products, I think this is a really nice method. Let's go ahead and distribute this 30 to both sides of this equation. If we go ahead and do that, we're going to get 30D plus, I think this is 450, is equal to 50D. Now, if you go ahead and subtract 30d from both sides, we're going to get 450 is going to be equal to 20d. And if you divide both sides by 20, the zeros can cancel out with each other. And then 45 divided by 2 is going to be 22.5, or the distance here would be 22.5. Now, what did we define d to be again? Let's go ahead and check back. D is representing the distance traveled for the slower car. So let's go ahead and say that this 22.5, or the we can say the slower car traveled 22.5 miles. And the faster car traveled, I think we said it was what, 15 miles further. So it would be 22.5 plus 15. That's going to be 37.5 miles. Now, of course, if you wanted to go ahead and check this, you could take this 22.5, you could plug that in right over here, and take the 22.5, plug it in right over here. You can go ahead and see if these ratios, or rates rather, are equivalent to each other, and I promise that they are. All right, so that just about wraps up this lesson on learning about ratios and rates, as well as applying those concepts to looking at proportions. If you found the video helpful, please consider giving the video a thumbs up and sharing with a classmate or friend who might also find it helpful. And as always, keep up the great work that you're already doing.